This session is on projectile motion. Before you watch this section, you should be familiar with the concept of a vector and how to resolve vectors into components. So if you're not already familiar with that, then you need to brush up on vectors first. But projectile motion is when you have an object that's moving through the air in 2 dimensions. So you have, up until now, in Chapter 2, we've been considering motion that was only either horizontal or only vertical. But if you want to talk about motion that is both horizontal and vertical at the same time, then that's called projectile motion, and we need to learn how to deal with that. Now, the key concept in all of projectile motion is that horizontal motion and vertical motion are independent of one another. That is key. Because what that means is that if I have some object with a velocity that is partly horizontal and partly vertical, like that, say, so that the vertical direction I can draw like this, and the horizontal axis I'll draw like this. So that vector that I drew obviously has both a horizontal part and a vertical part. What this key concept says is that I can resolve that motion into the x part and the y part, and once I've done that, those 2 parts of the motion can be treated independently. In other words, what I've done is I've separated a Chapter 3 problem, a projectile motion problem, into 2 separate Chapter 2 problems. One for the horizontal part of the motion and one for the vertical part of the motion. So let me give you an example of how that works. Okay, let's go ahead and stick with what I've already got drawn there. And let's say that this arrow that I have drawn represents a velocity vector of, say, 4 meters per second at an angle of 30 degrees with respect to the horizontal. Okay. And furthermore, let's say that that's the initial velocity that I gave some ball that I'm throwing. Okay, so if the initial velocity is 4 meters per second, 30 degrees above the horizontal, and this ball is going to go like that and land somewhere, because I'm throwing it, say, off the top of a building. Then let's say that the ball lands 1 second later. And let's say we want to find let's say we want to find how high is the building off which we threw this ball, And also, let's find the distance away from the base of the building that the ball lands. In other words, the height of the building, that would be this distance here. And the distance away from the base of the building would be this distance here. Okay, well, in any projectile motion problem, the first step is always to take advantage of the fact that the horizontal motion and the vertical motion are independent. So the first thing that you always do is you resolve the motion using vector components into the horizontal part and the vertical part. So the first thing we need to do is find v0x, which is the x component, or the horizontal component of the initial velocity, and v0y, the vertical component of the initial velocity. Okay, using trigonometry, then since v0x is adjacent to the 30-degree angle, and I already know the hypotenuse, then I need to use cosine. So we have v0x is equal to 4 meters per second times the cosine of 30. The cosine of 30 is about 0.87. We'll need our calculator for doing 4 times cosine 30. Okay, so times 4 cosine 30, that's 3.46. V0x is 3.46 meters per second. And v0y, because it's opposite to the 30-degree angle, then trigonometry says I need to use sine. So v0y is equal to 4 meters per second times the sine of 30. Sine of 30 is a half, so v0y is 2 meters per second. Now we've resolved the initial motion into the x part and the y part. That's always the first step when you're working a projectile motion problem. Okay, the second step is to write down the things that you know and the things that you want to know, just like if you're back in Chapter 2 working a regular kinematic equation problem. Except we have 2 different variables for each possible kinematic equation, because you'll have one set of kinematic equations for the x part and one set of kinematic equations for the y part. So whereas in Chapter 2, say we had v0, in Chapter 3 we have v0x and v0y. So what are the other things that we know? Well, in the y direction, we know that the acceleration is the acceleration due to gravity, and that's 9.8 meters per second squared down. And assuming that we're going to let up be positive as our sign choice, then that means gravity. The acceleration due to gravity is going to be negative, so we'll make it negative. Okay. So we know v0y, we know ay, the acceleration in the y direction, and we know time. Time is 1 second. What we're looking for is how high is the building. We'll call that delta y. Now, in Chapter 2, we called everything delta x, whether it was horizontal or vertical, but this time, since we have both a horizontal and a vertical, then we'll call delta x the horizontal displacement and delta y the vertical displacement. So we're looking for delta x on the x side, and we're looking for delta y on the y side. Is there anything else we know? Well, there is one more piece of information we have, and that's the acceleration in the x direction. The acceleration in the x direction is 0 because gravity does not pull things sideways, it only pulls them down. So we have something to accelerate the object in the horizontal direction, gravity. But because we don't have any appreciable air resistance, remember we always ignore air resistance unless I explicitly tell you otherwise. Okay, so since we don't have any air resistance and we don't, the ball doesn't have any engines or anything, there's nothing to accelerate it in the horizontal direction. So in projectile motion, the horizontal acceleration is always 0. That's the #1 mistake that people make on the exam, by the way, is that they forget that the acceleration in the horizontal direction is 0. So just keep that in mind, and maybe you won't be one of the people who make that mistake. So we've written down everything that we know and the things that we want to know. So we now will use the kinematic equations in order to solve for what we want to know. All right, I'm going to erase our key point up there at the top to make room for us writing down the kinematic equations. Okay, now kinematic equations in Chapter 2 applied for both vertical and horizontal motion, but we only used them one at a time. This time we have horizontal motion and vertical motion at the same time. Let's write down the kinematic equations, and then I'll show you how to use them for both horizontal and vertical motion at the same time. So we have delta x equals v0 t plus 1/2 a t squared we also have v equals v0 plus at, and v squared equals v0 squared plus 2a delta x. Now, we need to be able to use these for both x and y, so we actually need 2 sets of them. So what I like to do is to put a little x subscript here for v0x, and put an x here to make that the acceleration in the x direction. Okay, then you have v0x there, ax here, vx, vx, v0x, and ax. And then we'll write these again for the y direction. Delta y equals v0 y t plus 1/2 ay t squared. Vy equals v0 y plus ay t, and vy squared equals v0 y squared plus 2a delta y. Right, so after step 1, which is resolve the velocity into its x components and its y components. Step 2, write down what you know and what you want to know. Step 3 is pick one of the things that you want to know and decide whether that's an x question or a y question. Right, so if we pick how high is the building, clearly that is a vertical motion question. delta y. So we need to look at the set of kinematic equations that we wrote down for the y direction, these, and see which one should we use. So it looks like the first one is going to work. Delta y equals v0yt plus 1/2 ayt squared. So delta y equals v0y, we found that to be 2 meters per second. T is given as 1 second. Okay, plus 1/2 ay. Well, ay is a negative 9.8 meters per second squared. And we have t squared, that's 1 second squared. So delta y is equal to 2 meters, because the seconds cancel. 9.8 times 1/2 is 4.9. Times 1 squared is still 4.9, so that is minus 4.9 meters. And that gives us a negative 2.9 meters. So it means that the building that we threw this ball off of is 2.9 meters tall. The negative sign makes sense because the negative means down. It means that the ball landed about 3 meters lower than the place from which we threw it. So we expect that that would be negative, right? You expect that the ball is going to go down, not up, when it lands. All right, how about the other part of the question? Find the distance of the building from the base. Well, that's delta x, the displacement in the x direction. That for x questions, we use this set of kinematic equations. And again, the first one will work. But it's even easier this time because a sub x is equal to 0. If delta x is equal to v0x, v0x we found to be 3.46 meters per second times time, 1 second, plus 1/2 axt squared, but ax is 0, so that whole term is 0, and we get that delta x is equal to 3.46 meters. And we're finished with that problem. Okay, I am going to clear this page, so pause if you need another moment to write something down. I'm going to clear this page and give you a conceptual question to think about. Okay, our conceptual question is this. Let's say that we have 2 balls up at the top of this building. One ball, ball A, we will drop from rest. Okay, we'll give it an initial speed, v0 equal to 0, and it falls and eventually hits the ground. Okay, at the same time that we drop ball A, we are going to throw ball B. But I'm going to throw ball B in such a way that it is moving horizontally initially. Okay, so its initial speed, v0, is 2 meters per second, but it is all to the right. There's no vertical component to that initial velocity. Okay, so that ball will, of course, land over here somewhere. Again, I throw ball B at the same time that I drop ball A, but I'm throwing ball B horizontally. So the question is, which of these lands first? Is it ball A, ball B, or do they land at the same time? So I recommend that you pause the lesson, think about this for a moment, and try and come up with an answer. Try, pretend you're trying to convince your buddy of the answer, and what physics principle are you going to appeal to in order to justify your answer. And then when you've got, when you think that you've thought it through fully, you can unpause and I will tell you the answer. Okay, the correct answer is C. They land at the same time. Again, we go back to the key principle of this chapter, which is horizontal motion and vertical motion are independent of one another. That's the key for the whole chapter. It's also the key for this question. What that principle means is that the horizontal motion of ball B is irrelevant in determining how long it takes to hit the ground. Because how long it takes to hit the ground, that is a vertical motion question. And vertical motion is independent of horizontal motion. So the fact that ball B is moving to the right when I throw it is irrelevant as to how long it takes to hit the ground. What matters in how long it takes to hit the ground are two things. You need to know how high, how far does it have to fall, delta y, and that's the same for both A and B. You need to know the component of the velocity in the y direction, but the component of the initial velocity in the y direction is 0 for both ball A and ball B. And of course the acceleration of both ball A and ball B is 9.8 meters per second squared down. So everything about the vertical motion of these two balls is identical. And since horizontal motion is independent, that doesn't matter. They both hit the ground at the same time. Choice C is the correct answer. Okay, that will be all for this lesson. I will post another lesson containing more examples of projectile motion a little bit later. So look for that one as well.